Hi everybody. In this brief video, we're going to talk about the energy stored by a capacitor. So in the previous two videos for chapter 25, we've talked about capacitance and actually derived formulas for it for a parallel plate capacitor and a cylindrical capacitor. In the second video, we talked about how to combine capacitors in series and parallel in a circuit. So in this video, I want to talk about or calculate or get a formula for the energy stored by the capacitor. As the charge builds up on the capacitor, you can think of it as an energy storage device because you get the charge on the capacitor, it's just sitting there. If you release it suddenly, there's a lot of energy, a lot of work done by that charge that can be used in other ways. Creating microwaves in a microwave oven, for example. So what we want to do is be able to calculate the amount of energy in that capacitor when it's fully charged. So in our circuit, we have our battery and we have our capacitor. Now, in fact, in reality, we'll find in the next chapter that there's also a resistance of these wires, or sometimes even put a resistor in here. But mainly what we do is we charge up the capacitor by pushing charge from the voltage onto the plates, right? So eventually you end up with a positive plate and a negative plate, and you have a certain amount of total charge Q on the capacitor. What we have to do to calculate the energy stored by the capacitor is to calculate the amount of work done as you push a little tiny piece of charge through here. Now, remember, first of all, that our definition of capacitance is that the total charge is capacitance times the voltage. Now, this charge may change as I build up charge, right, until I get to the maximum amount. So what I'm going to write this as is little q equals CV. So I'm taking little amounts of charge and moving them onto the capacitor, and eventually I build up to the total amount of charge. Now, as I do this, imagine that I have a little bit of charge on the capacitor. Well, if I want to actually get a little more charge, what I would do is I would have to do a little bit of work. And remember, work and energy are related to voltage by the fact that I just multiply the voltage by the test charge. So now I'm going to say I'm moving my little dq amount of charge, I'm pushing it onto the capacitor. My voltage is constant, it just comes from the battery, right? So charge times voltage equals work or energy. Now, if I want to get the total amount of work done to build up to that total charge, of course, right, I've got dq's, I just integrate. So I'm going to integrate from 0 to my total charge here. And I'm going to remember that Q equals CV, or for each little amount of Q here, V is Q over C. So I end up getting this integral, 0 to capital Q, total charge, times dq, and then V is Q over C. Right now, the left-hand side is just the work. Now, this is like Q dq, right? Capacitance is a constant. It's a property of the geometry of the particular capacitor. So it can come out, and I just have integral of Q dq. Well, that's just Q squared over 2. So I end up getting, finally, that the total amount of work done is 1/2 Q squared over C. Now, I could write this in a different way, right? If I plugged in Q equals CV, capital Q, I could write this as 1/2 CV squared, all right? So this is really the formula for the work done to build up the capacitor to its total charge, or you could say it's the energy stored in the capacitor when it's at its maximum charge there. Now, of course, I haven't talked about what type of capacitor this is. This formula actually is general. It works for any type of capacitance. But let's consider a parallel plate capacitor for a moment. And if you remember, in a parallel plate capacitor, a couple things. The electric field between the plates of a capacitor is sigma over epsilon zero. Now I'm using the epsilon zero permittivity constant instead of my K constant. But also we found previously in the first video of chapter 25 that the capacitance is epsilon zero A over D. So what I'm going to do is just plug these in, right? And again, E here is electric field instead of energy. I think in the book you might see this written as U. It's kind of potential energy. But I'm going to plug these in, right? So I have my energy, or my U, is 1/2 times epsilon zero A over D, for my capacitance here, times my V squared. Now V, remember, also is electric field times distance between the plates. All right, so I'm going to plug that E squared D squared in here for V. Right, I just plug that. So I can cancel one of the D's here, and what I end up getting is that U is 1/2 epsilon zero A times D times electric field squared. So first of all, we see energy is proportional to the square of the electric field. This will become a more general thing too if you go into electromagnetic waves, which will not actually appear in this class until physics 223. But anytime you have an electric field, one thing you can think of is the energy is sort of stored in the field. So for our capacitor, right, we've got an electric field between the plates going from positive to negative. And what you could think of is that there's energy somehow spread throughout the area between those plates, or the volume. And if you look, right, the area of the plates is A, the distance D. A times D is really the volume. And so what I could write this as is that the energy per volume, sometimes you'll see it as little u, is equal to 1/2 epsilon zero electric field squared. So sometimes people will call this the energy density. It's a new way of looking at energy, really. You can store energy throughout an electric field. So there are electric fields all around us due to our electronic devices, cables, stuff like that. You can think of energy being stored in that field. And this is the formula to calculate the energy per unit volume, or energy density, of that field. So that's the energy. This is the last video for chapter 25. We'll go on to chapter 26 after this. But hopefully that will help you get through all of the problems with chapter 25.